In the last video, we explained GUI space, the GUI toggle, icon, and highlighter. Today, we'll explain how the GUI root brings all the controls together. The GUI root is named as such because it is at the root of a tree that is formed by the nested GUI controls. This image displays a simplified version of the tree that is formed by the options screen. The GUI root has an icon, text box, button, and toggle as its immediate children. The toggle has two buttons and a text box as its immediate children. In the configuration file, everything that is not the GUI root is an immediate child of it. The children of its children are only instantiated in the GUI controls concrete class, assuming they have any. The GUI root class is a GUI widget. It is also a singleton with a max of 2 instances. I use one for the main display and another for my level editor. It is also a parser, so it can read in the GUI screen configuration files. As we scroll down the function declarations, we see functions for dealing with cached screens, viewports, creating controls, and converting between spatial coordinates. They are followed by the widget and parser virtual functions we will overload. We will explain them after we explain the member variables. The viewport specifies the position and dimensions of the viewport in window space. Window space is measured in horizontal and vertical pixel length. The viewport offset determines how far the viewport is from the bottom left corner of the window. The viewport portion specifies the portion of the window the viewport occupies. The level editor's viewport takes up 25% of the window's pixels and is located at the right of the window. The process input boolean allows us to turn off input processing in the main viewport when the level editor is active, and vice versa. The process message boolean allows us to suspend the processing of GUI messages. This is particularly useful when the stage selection menu is scrolling. We have a map of GUI screen caches that are referenced by a string. The string is the name of the GUI screen configuration file. The GUI screen cache class holds an array of pointers to GUI widgets and a variable to determine its current count. The constructor sets the pointers to null. The destructor deallocates the widgets. Highlighter ID is used to specify the name of the visible GUI highlighter. It is possible for there to be multiple highlighters defined in a GUI screen configuration due to differing sizes of GUI elements. My level editor GUI screen is an example of this. The cursor ID screen is used to identify the cursor icon. The string is just cursor with a capital C. The parse tokens are used for reading the values specified in the GUI screen configuration files. The active control indicates which GUI control has the focus. Whichever control has this is the only one that can currently have its functionality invoked. The GUI texture IDs array is for holding the texture IDs for all textures used by the graphical user interface. The num texture IDs specify the amount that have been loaded. The following 5 integers indicate the number of widgets of each type that have been loaded for the current GUI screen. The load to cache boolean indicates whether the GUI screen we are currently loading will be put in the GUI screen cache or not. The constructor sets the default values. The initialize function initializes the parse tokens for the GUI controls. The first parameter represents the name of the structure. The second represents the class or data type we want to set. We set the viewport portions of this GUI root to 100% for the length and height. We then call calculate viewport to set the viewport values. Create button makes sure that we have not surpassed the max controls per type before allocating a new button on the heap. We set the ID and file name for reference. We'll use this data to identify elements for deletion later. It then adds the button as a child of the root before calling its initialize function. All the other controls follow the same logic. Delete children is called anytime a GUI screen is no longer needed. For example, when we go from the main menu screen to the stage selection screen, we pass in the name of the GUI screen file to this function. We iterate through all the children of the root, checking for the ones that hold the same file name. If any of them do, they are removed from the linked list and their memory is deallocated. The decrement count function decreases the count of controls based on the type that was deleted. If the widget has children, these are deleted in the widget base class destructor. The cache screen function checks if the file name is empty or null and returns if so. Because we have different GUI screens based on the current language, we set the name of the GUI screen cache to the language folder and then append the file name. If it is already in the cache, we return. Otherwise, we read the data file with the load to cache boolean set to true, which indicates that we do not want to display this screen immediately. Free memory is called when the game is exited. It deallocates the widgets, cached GUI screens, and parse tokens, and resets the counts for each control type. The free textures function is not currently being used. I find it more optimal to leave the front-end textures resident in memory until the game is closed. It keeps the textures for the cached screens available. If you are within your memory budget, this is fine. The setActiveControl function is called whenever we want to change the control that can have its functionality invoked. For instance, when we are iterating through the options in the pause menu, or when we transition to a new GUI screen and want to set a control as the default active one. The function first checks whether there is already an active control by seeing whether the pointer is valid. If so, it changes the text color to normal to indicate that the control is no longer active. After setting the new active control, we change the color of the text in the toggle or button to the highlight color. The button selection also places the highlighter at the active button by calling the activate function. We call hide other highlighters to ensure other potential highlighters are not visible. We sometimes have multiple highlighters for different shaped GUI controls, such as in the level editor. Set visibility of children sets the visibility of all the children from a GUI screen using the file name of the GUI screen as an input parameter. It is useful when I want to hide or display the rendering statistics, for example. Resize All sets the size of the GUI Roots model and then scales and positions its children. The GUI Root is not currently ever visible, but we still use its model transforms to scale its children relative to it. We update the position of the highlighter because the scale and position function might have changed it. The clear cache function deallocates the GUI screen caches. The read data function also checks if the screen is already in the cache. If it is, it loads the screen, then returns. It should be noted that this function and the previous are not always called together. The load cache screen iterates through the widgets pointed at by the GUI screen cache pointer and calls the create function based on the control type. For the GUI control, we just set the values directly because we're already in the class. This function leads to a more responsive front end. Because the textures have already been preloaded, they are the bottleneck regarding fast loading. At the end of the function, we set the active control to the first button or toggle we find, assuming we have any. Back in the vReadData function, we return true to indicate success. The GUI screen configuration files are in the front-end folder under the language-specific folders. If the screen is not in the cache, we create the full path by adding the front-end folder string to the current language folder, then appending the file name. We use the ifstream instance of the parser base class to open the file. If that succeeds, we begin parsing the file and instantiating GUI controls as they appear. The parseStructure function calls the parser's base class virtual function vCreateStructure. The createStructure function checks for the name of the structure we want using conditional statements. For each control, there are two conditions, either to write it into the screen cache for use later or to instantiate it for use immediately. In the former case, we search for the GUI screen in the cache screens map using the allocate or set cache screen function. If it is not present, we create a new instance of the GUI screen cache and use the file name as the key to create a new element in the map. In the second case, the GUI Root's model member variables are set directly. The same logic follows for the button, icon, highlighter, text box, and toggle. At the end of the function, the final conditional prints an error message to the console and triggers an assert if a valid structure name is not encountered. Back in the readData function, at the end of the do-while control structure, we check whether we are at the end of the file. If not, we check for invalid characters that might be erroneously placed in the file. An invalid character in this context is any which is not a tab or a space and therefore has a visible representation. After we close the file, we set the active control to the first button or toggle that we find. The other readData function returns the full path name of the GUI screen for the current GUI screen to reference. The saveData function is empty because currently I write the GUI elements directly into the GUI screen text files manually. When the real-time GUI editor is complete, this function will save the GUI editor's controls to the GUI screen class's configuration file. The processMessage function handles messages sent directly from the front-end manager. The front-end manager manages the two GUI roots, one for the main view and one for the level editor, and all the GUI screens at the class level, as opposed to all the controls of the GUI screen class as the GUI root does. Examples of the class it manages includes the main menu screen class and the option screen class. I'll explain it in more detail in the next video. We make sure there is an active control because otherwise there is nothing for us to process messages for. If the Start Released message is sent through, it means the Start button on the gamepad or the Enter key on the keyboard has been released. We set the current active control's selected boolean to True. We return immediately after because we only want to invoke the functionality of one control per sent message. The Up Released message is sent when the up section of the D-pad is released or the up arrow key on the keyboard is released. The player is probably trying to iterate through a selection menu of some kind, so we ensure that there is more than one child by calling getNumberOfElements of the widget's linked list. We check if the vertical flow boolean has been set to true, which, if it has, means buttons or toggles are arranged vertically and sequentially in this screen's configuration file. Looking at the main menu configuration file and remembering in GUI space that +1 is at the top of the screen and -1 is at the bottom, we can see the buttons listed in vertical order by looking at the second coordinate of the rectangle structure. Because they're also listed sequentially, they can be iterated through intuitively in the menu as so. The flaw with this system is that it is not flexible enough. A better system would iterate through the controls based only on their spatial positions. I might add this functionality in the future. Back in the processMessage function, we check for buttons or toggles to set as the current active control. The down-released message works in the same way, but it iterates forward through the linked list. The left and right released work the same way for interactive controls that are placed horizontally. They also set the right or left arrow children of the toggle to selected. The toggle class doesn't currently work with vertical input. At the end of the function, we recursively call the process message function for all the GUI Root's children. If one of the children is active, then their corresponding functionality can be invoked or a mouse-over interaction can be processed. The update function calls getChild to ensure that a control with the cursor ID string is present in the linked list. We call the getMousePosition of the input manager. On Windows, this function calls getCursorPosition, which retrieves the cursor's position in screen pixels, irrespective of where the application window is on the screen. We then call screen-to-window to convert the screen position into a position that is relative to our window. Window space is also in pixels. Its world origin is at the top left of the window as 0 on X and Y. Any position to the left of that position is negative on X, and anything above is negative on Y. To obtain the position of the window, we call the Windows Screen-to-Application Window function of the Windows API Manager class. This class manages the setup of the application, the running of the main update function, and Windows operating system specific window creation and configuration. The Windows Screen-to-App Window function gets called in the Windows Procedure function whenever a window is resized or moved, both of which will happen upon the creation of a window. If the size message is passed through, we obtain the window's height and length using the high-word and low-word Windows macros. These macros are defined in the mid-win-def header file. They allow us to retrieve data related to the current Windows message. We ensure neither of the values are 0 to avoid division by 0 when we calculate the aspect ratio. The Windows Windows-to-App Window function adds half the screen's X resolution to the X ordinate and minuses half the screen's Y resolution to the Y ordinate, so that we're referencing the center of the windows rather than the top left corner as Windows does by default. If the window is at the center of the screen and the screen's resolution is 1080 by 1920, the position will be 540 on X and 960 on Y. Upon a Move Windows message, the low and high word macros give us the screen position in unsigned long integer values. If the top left corner is beyond the left boundary of the screen, we get a negative value, but in an unsigned long, we subtract 2 to the power of 16 to remove the high-order bits that contain the sign information. We could also just cast the result of the low and high words to shorts to achieve the same result. Back in the GUI root, we now have the position of the cursor in window space. We now call window to viewport to convert to viewport space. This function subtracts the viewport position from our coordinates. For instance, if the viewport's X position starts at the 100th pixel and the current cursor X position is 0, then the transform position would be minus 100, meaning it is 100 pixels offset from the left of the viewport. It's only needed for viewports that do not start from the bottom left corner of the screen, such as my Level Editor's viewport. We then call viewport to orthographic world to convert the coordinates into OpenGL orthographic world values. We ignore the z-axis because the GUI is two-dimensional. We subtract half the viewport length and height to convert from the viewport's origin at the bottom left of the screen to the world's origin at the center of the screen. It's a simplified algorithm because it assumes the camera is at the origin of the world looking down the negative z-axis. Finally, we set the cursor's model position to the final conversion. Rendering Rendering the GUI element starts in the render function of the game class. The front end is rendered second to last because it needs to be rendered on top of the in-game elements, particularly in the instance of the heads-up display. The render front end function uses orthographic projection because depth-based rendering is unnecessary. The orthographic projection uses half the negation of the viewport length to set its left value. It uses half the value of the length to set its right value. The bottom and top values follow the same logic. This places the center of world at the center of the viewport if the camera is looking through the origin of the world, which it is. The setViewport function calls the OpenGL function GLViewport. SetView calls GlueLookAt. We enable blending for images that need transparency and set the blend function to source alpha for the source and 1 minus source alpha for the destination. This means that the image we draw will blend in proportion to the alpha value of the image and whatever the image is drawn on top of. For example, if the alpha value for the source image is a red square and it has 0.5 for its alpha value and it is drawn over a blue background, the result will be a purple-looking square. We disable normal arrays because we don't use light-based rendering for the GUI. The render GUI function takes in a GUI widget as its parameter. We pass in the GUI root so we can render its children. First, we render the model, which is a quad with a texture attached. The enable array function calls GL-enable client state with GL texture coordinate array to allow the usage of texture coordinates. Bind surface calls GL use program with the surface ID to attach the shaders for the upcoming draw call. setMaterialAlpha calls GL uniform 1F to write to the alpha value address in the shader. setVertex and texture pointers sets the arrays that the draw call will use. setTexture calls GLActiveTexture to make the texture unit active, then GLBindTexture with the texture target of GLTexture2D. The drawModel function uses the inbuilt OpenGL transformation matrices. Since I am not currently using rotations, an optimal function could be created that only has the translation and scale matrices present. The unbindSurface function calls GLUseProgram with 0 to detach the shader. Next, we call the widget's render function, which may have other elements that need to be rendered, such as text for controls that use GUI text boxes. We render the bounding box of the widget for debugging purposes. After that, we recursively call the render GUI function for the children of the GUI root. The consequence of this implementation is that the children are always drawn on top of the parents. In the next video, I'll explain how the front-end manager works. Thank you for watching.